Here is a pipe, and here's another one. Have you ever wondered how engineers know how big or small a pipe needs to be for a specific application? If that is the case, you are watching the right video because today we're going to find out. Hello, my name is Alex. I'm a process engineer with many years of experience in the industry. Today, we are going to explore the world of pipe sizing. We will discuss a powerful tool called Line Sizing Manager within Aspen HYSYS. This is a tool I've relied on for many years to simplify and streamline my designs. By the end of the video, you will not only grasp how to use the tool, but also understand some of the factors you need to consider when sizing pipes. Plus, I will share tips on crafting effective calculation documents to clearly communicate your design decisions. You will also be able to create calculation summary sheet documents that looks professional, such as the one that you can see on the left-hand side of the screen. This will show all your main inputs and results, which you have used to determine the proper pipe size. Before we probe into pipe sizing, let's talk a little bit about the term called pipe sizing criteria or design constraints. Pipe sizing criteria is all about choosing the right pipe size based on factors such as flow rate and the system pressure requirements. The two most fundamental line sizing criteria that you will always use when you do your calculations would be the maximum allowable pressure drop and the minimum and maximum allowable flow velocity. Now let's break down each and every one of those. The maximum allowable pressure drop is the acceptable pressure reduction as the fluid flows through the pipe. Keeping the pressure drop within acceptable limits ensures that the system operates efficiently and, most importantly, it operates cost effectively. The velocity constraint sets limits to the fluid speed to prevent materials from settling in the pipe and also to reduce erosion of the pipe walls. Now let's apply some of these concepts. And to do that, I've put together a design case study. Now, picture yourself as a process engineer tasked with creating a water transfer system. The goal is to transport water from a tank to a heat exchanger that is located 350 meters away. The key challenge is to maintain a flow rate of 15 cubic meters per hour with an initial supply pressure of 1000 kPa, while ensuring water arrives at the heat exchanger with a minimum pressure of 400 kPa. Here is a simplified sketch to visualize our problem statement and assumptions. On the left-hand side, we have water storage tank and an isolation valve on the outlet of the tank, and the distance between the heat exchanger and the tank is roughly 350 meters. And as we were told in the problem statement, that the minimum required pressure in the heat exchanger is 400 kPa, and we have to maintain a flow rate of 15 cubic meters per hour. Now that we understand the requirements for the sizing of this pipe, we can jump over to HYSYS and continue with the calculations. Okay, now that we are in HYSYS, we're getting our component. That's water, for example, and the fluid package, since we are dealing with water, would be ASME steam. Then we go to the simulation environment. Since we're modeling a pipe, some might assume that we would be modeling a pipe segment, but that's not the case. We actually can size pipes without even modeling any pipe segments, and how we do that is I'll show you through the next step. We put in the material stream. I'll call this one feed water, and the temperature is 25 degrees. The supply pressure 1000 kPa, and the flow rate is 15 cubic meters per hour. The composition is pure water, so the mole fraction will be just 1. Now we have fully specified the material stream. What you can do now is come to this tab here, attachments, analysis, create, and you look for line sizing manager, then you add one. And this is where most of the calculations will be done. Rename this to base case. This is going to be looking at the design conditions as they are, the specified flow rate and the pressure. Since we are doing a calculation for design, this is a brand new line, so we just are doing a design calculation. Otherwise, it would have been a rating calculation for an old pipe or an existing pipe. We are going to assume it's no design margin. We're going to size for 15 cubic meters per hour pipe material, carbon steel, schedule 40, and the sizing criteria, we're going to insert the criteria in the next step here in the settings. And the pipe length, we don't know exactly the length of the pipe run, but we know that the 2-unit operations are about 350 meters apart. So as a start, I would assume 380 meters of the actual pipe run. And then in the pipe, we have a few fittings. We'll insert the fittings here. We'll go to edit, add fittings. And we know we've got ball valves, 2 of them, one at the inlet, one at the outlet of the line, and press enter. Sometimes you really have to press enter for the program to accept the inputs. And we insert another fitting. The line will need a few bends. I'm assuming 5 bends, but it can be any number or any other fittings close to that. That's all the input you need. Then you go to settings to set your criteria. The criteria, based on discussions earlier, we said for water or for liquid systems, anything between 1 meter per second to a maximum of 4.5 meters per second should be okay based on industry standards. I normally designed for 80% of the maximum. So 80% of 4.5 will be around 3.6 meters per second. Once you press enter, the whole line is sized. The results will be seen here on the details tab. The first thing that your eyes will want to is this. That's the pipe, the nominal pipe diameter, 40 mil or 1.5 inch. This is the actual velocity within the line, the maximum velocity that we specified, 3.6. It will tell you whether you've met that criteria. In our case, we have met the criteria. The pressure drop in that line is 1050. The pressure drop is greater than the supply pressure. Liquid gets to the inlet of the heat exchanger is 400 kPa. You can assume that the pressure can be increased via a pump, or you can size this line such that this pressure drop is not so big, and which is why we're here today, to size a line that does not need a pump, but it is able to deliver the minimum flow rate that is required, as well as meet the inlet pressure of the heat exchanger. We come back here, specify a pressure drop criteria. Remember, the supply pressure was 1000 kPa, and the minimum inlet pressure in the heat exchanger is 400 kPa. So what that tells me is about 600 kPa pressure drop in the 380 meter line. So if we take the ratio of the pressure drop, that's 600 kPa divided by 380 meters. So that will give you approximately 1.5 meters kPa per meter. That's the maximum pressure gradient you're allowed to have on that line. And now that becomes another design criteria. The program is going to size the line now looking at those 2 criteria. It will pass the pressure gradient and also pass the flow velocity. The calculation is done in the background. Then you go to your details. The line size has gone up 0.5 inch. So from 40 to 50 mil, now total pressure drop is about 296. That means by the time this fluid gets to the heat exchanger inlet, it will be at around 700 kPa, which is good. Now, you want to look at other cases, right? Because the problem statement did say consider future needs, meaning one day we might want to increase the flow rate through that line. To model those cases, I just come here and clone what you've got here, your inputs, clone the line. Let's assume now we're going to increase the flow rate by 10% flow margin. You can label whatever you're comfortable with. And then in the flow margin, you increase that by 10%. And you'll see the line is still good at 50 mil. Even if you increase flow by 10%, the 2 inch will still do the job. The pressure drop will go slightly higher, but you'll still be able to meet the minimum pressure required in the heat exchanger. Now let's do another case. We'll clone the same. I've already done 3 cases by just doing this method. Increase that by 60% flow margin. You can have as many cases as you like. Increase the flow rate or the flow margin by 60. Now let's see what happens. Now, if you increase the base flow by 60%, it needs to be at least 2.5 inch, right? And the 2.5 inch, your pressure drop will be 296, which is pretty much the same as that. You'll still be able to meet the inlet pressure going into the heat exchanger. But a tip, in practice, a 2.5 inch line is not really common. Yeah, it is a standard pipe size, as you can see from the tables here. It's a standard pipe, but you don't really necessarily find it off the shelf that easily. And what makes it even more complicated is if you were to put valves and other fittings, it will be very hard to find a valve that is a 2.5 inch from my experience. So what I normally do, I'll go to the next size up, which is a 3 inch, which is common. Most of the valves and fittings will be off the shelf. Once you've done this, to communicate your design, you just click here, print data sheet. I prefer to just show the sizing and the settings. Then you set up your preview before you print. This is what you're going to end up with. A data sheet that shows your base case, 10% flow margin, 60% flow margin. It shows the most critical results. The only time you would need to increase that line to at least 2.5 inch is if the flow was to increase by 60%. And then you can talk about the pressure drop across that line. In your calculation sheet, you specify what the pressure criteria and the velocity criteria used. Look, I try to cram as many things as I can, and I hope you did learn a few things out of this. Look out for more videos coming and let me know which topic you'd like me to cover. I'll see you in the next video. Bye.